Our next session is going to be about the CAPI SNAP demonstration. It's a real-time demo, and also we are going to use the Nimbix infrastructure for the demo. Alex from IBM is going to be presenting that. Alex.
Thank you, Alexandre. Nice to meet you all. My name is Alexandre Castellane. I'm working in France with the Montpellier department, in the cognitive department, and I'm very glad to be here. First of all, I'm very glad to be by Nimbix because that's a year I'm using with lots of success their system. So I want to thank you guys very much for all the job you've done and for the performance that you are achieving in terms of network availability and making machines working so nicely for us. So thank you very much to you.
Thank you.
Okay, thank you to all of you. Let me switch to the presentation. So what is, we have two screens. We just make sure I have a mouse here. Maybe I can move here. Okay. All right. So this is it. Okay. So first of all, I have a few questions for you. First question is, who knows what an Fpga is? Okay, so let's say roughly a bit more than 50%. Okay, who has used an Fpga? The same ones? Usually you don't when you know. Okay. Who knows about HLS? HLS in general, not specifically Xilinx. So okay, this is a little bit the ratio of the knowledge. HLS is very briefly a tool that allows to program in high-level languages like C or C++ and provide things to go into the HLS. So I'm just speaking to the guy who knows Fpga for the moment. Who knows CAPI? Okay, not everybody, all right. OpenCAPI? Okay, all right. SNAP, the main topic I will talk about, all right. Nimbix platform? Everybody raise his hand? Okay. Yeah. And Fpga acceleration is a deduction of all these things. So since we have different level of knowledge, let me go very quickly on the basics and then we'll go on the machines. So what an Fpga is a bunch of logic. So when you buy a computer, a microcontroller, microprocessor, you get an ASIC. That means that the supplier has built everything, hooked up everything, and you cannot change that. You buy a P8, you buy a Ethernet controller. That's a generally low cost for the performance, but you get a fixed logic inside. Okay. For Fpga, you get a sea of gate, a sea of logic, a sea of registers, a sea of flip-flops, a sea of part of single piece of memory that is not interconnected. And then you need to describe what you want to do with this sea of gate. So it's like an ASIC that has not been finalized with all the routing to make things simple. So it's up to you to decide how you want to route the logic to make a small microprocessor. You want to embed an ARM inside, so you need to describe how your registers are connected to make your accumulator and so on. Once you have described that, you make functions. You are not obliged to utilize all the logic. The larger the Fpga and the smaller the function, then the more waste you have. But that's the deal. You get a part, more or less big enough for your application, and then you build some logic, so you have to describe it. And the guy who knows Fpga knows that describing the logic is a specific hardware engineering task, and it can take time. We'll see how we address that. The SNAP we are speaking about, it's a higher level. It's just difficult to match the different level of your knowledge. The SNAP is a framework that IBM has developed in open source to ease the process from going to a sea of gate into a system that is doing your function, that might be your functions, but it also includes the connection to the Power 8 or Power 9 processor. So it will also build for you the logic that you need. This is your responsibility, but this is the responsibility of SNAP. Sorry. Okay, so we begin to see some words. The advantage of my presentation is that we are taking several technologies. First technology is Power. The second one is CAPI. So CAPI in Power is, my colleague has spoken a little bit about that, is a very fast link And the goal in P8 was to establish a new link independent in OpenCAPI it will be independent of PCI Express, but the goal was on PCI Express using the hardware to make sure that a known card that is recognized by the system at power on is not anymore known as a PCI card, but it can be known as a CAPI card. What it means is that there is a specific link, I cannot go into these details because it's not the goal of the presentation, but there are specific hardware inside the processor that is connecting, as my colleague, our colleague has just said, making sure that the host is talking with minimum latency to the external I/O card that you can have. It can be a GPU, it can be an FPGA, okay? And using CAPI with our SNAP framework plus the HLS, which is the nice tool that several companies have built, and we are using the one from Xilinx, but there are several of them, taking some C description of your function and able to describe a logic to put in the FPGA. And all these four things make a very nice application that I intend to demo. Okay, I will not go very deep in detail, but see your host with several cards, okay? For CAPI technology 1 and 2, and the 3 is named OpenCAPI, is coming. For CAPI 1 and 2, we are using the same slots as the PCI 1, okay? We are using, CAPI 1 is using Gen 3 capability, and CAPI 2 is using Gen 4 capability for those who are knowing the speed of PCI Express. And on this layer, on this physical layer, we just ignore them, just for recognition of the card, we use PCI Express, but then we do not rely on PCI Express, we have our own connection. And the extension of that is going faster than PCI Express, so we are already at Gen 4, and we do not want to depend on PCI Express, so we have introduced like a CAPI 3, which we call OpenCAPI, because it's not anymore locked by IBM, it's open. So OpenCAPI is a third level of CAPI, which is, say, Gen 5, but it's not Gen 5, it's just 25 gig speed, and it's nothing to do anymore with PCI Express. Your card will be plugged into a PCI Express slot just for getting the mechanical aspects and the power supply. Are there any questions on that? Because I want to close the CAPI subject. Very quickly. Very quickly. No? Okay. Oh, I thought you said no. So you have two options to accelerate a function. Either you take an FPGA, which will offer new IOs, and my colleague has spoken about that. This is very interesting to bring IOs to your computing system, like very fast Ethernet, local memories. We will see that this one doesn't need memory because the speed and the latency to reach the processor makes the host memory visible from the FPGA. So we don't need any more DDR on the card, which is very, very interesting. And for sure, the second option is to have a GPU. It's not a comparison saying one is better than the other, but there are different things that we can do. And for example, in terms of power consumption, this guy, because it's making dedicated calculations for you that you have decided to build inside this FPGA, it consumes much less generally than an equivalent function that will be run in GPU. For sure, GPU have advantages and FPGA have advantages, and these ones are well known because they are programmed for years now, so it's very well-known technology. Okay, so I cannot go into the details of how we use that. I just want to make a comparison for how SNAP is programming your FPGA. No kidding, an FPGA engineer is really in front of this kind of machine. Okay, he has to trigger the clock timings, he has to organize the logic and so on. So it's not an easy part. The goal is that when you are a software engineer, you need to have a copilot, which is an hardware engineer today, if you want today, like before having HLS and SNAP and so on, before we mixed up all these four components, you need to have an hardware engineer, and it is a very long process to learn how to build these machines. Okay? So you need a specific hardware language, somebody who knows that. You need to hook up all your hardware functions. Remember this small part that is connecting to the power? This needs to be connected to your logic. Somebody has to do it. So this guy is required to do it. And you need also it's a big pain. You need, when you prepare a hardware description in FPGA, you need to prepare a bench, a test bench. That is, you need on the side to say, what if I'm providing a video to this uncompressing block? So you need time to prepare the uncompressing block. You need time to hook up that to the host memory into your FPGA. So you need to build a complete system, and then you do not have a connection to the Power 8 or to the x86. Then you need to emulate and say, okay, let's imagine I provide by simulation a video to this uncompressor. How things are going, at least from at the beginning. Is it taking care the right operation in the right order? Do I have timing concern and so on? And that is a nightmare because it doubles the job to do an FPGA. So the goal with all these four components together, good power technology, conversion from C to RTL. RTL is a language describing the gate. CAPI, which is a fast link between the FPGA, the I/O in general, and power, and SNAP, the framework we will demo. We intend to reduce that to a gliding machine. It's just a joke because I'm a glider pilot recently, so it just simplifies the way you reduce the number of operations, and it really is. And thanks to Nimbix, it's really something that you can access very friendly. It's very friendly and it's very inexpensive. But the goal is that you keep the same machine behind you, but you reduce to a very little number of elements, the things that are required. And then you can, please do not fire him because I'm a hardware engineer, but you can have him on the side and say, in case of problem, can you help me? But then this software writer, source knowledge, he can pretend after some training, he can pretend to glide the machine himself, having the power, the motor power behind, okay? It's just a... So without SNAP, with SNAP, you have no extra test to write. That's very important. We'll see it on the machine. You can directly simulate the exact description that you have put in your FPGA in simulation, and that's huge. Your application is a test bench, and you can concentrate on your code, and some of the painful things are removed. The SNAP and CAPI concept is the following. We have extra external IOs, which are today connected to a regular CPU, connected to its host memory. If we introduce an FPGA, we can have several actions. Today the SNAP is supporting one action, but the architecture is aimed at supporting several actions should there be a need. And it's open source, so you can also develop yourself. The FPGA can have access directly to these IOs. So there is no need for the CPU to be using time to access that. You can go through the FPGA. So FPGA is providing a new I/O library, a new I/O access to the processor. The CAPI is providing very fast link, and this fast link includes coherency to the memory. So it's very important. I cannot go into the details, but please ask questions on the side. I can give you get my name. CAPI is very good technology because the hardware inside, on the side, will allow the FPGA to talk directly with the same address as your program is talking. So no conversion. It's all handled by hardware. So it's very fast. The SNAP is the logic and the environment that we offer on GitHub for you to make all this source working. And we are not obliged, but we can use Evalue HLS, which is the HLS tool from Xilinx. HLS again is the converter from C to RTL. RTL is a hardware description. And all this, and you miss one element, then you kill the nice thing that we have built. Okay, let's go very quickly over that. All right, so when you have a card, and this is what we will demo on Nimbix, we will use a Power 8, and the good thing on Nimbix is that you can train on Power 8, but whatever you do on Power 8 will be reusable in Power 9. Power 8 is using CAPI 1 technology, then Power 9 is offering CAPI 2 today, and OpenCAPI tomorrow for the SNAP, okay, let's say early 2019. But whatever you do today on the Nimbix platform, on your platform, because Power 8 is very inexpensive today, can be reused. That is, all these hardware connections is not dependent on the power that you are using. So the investment is valuable. You spend, let's say, few days, it's only few days to discover this SNAP environment. These few days you can rely on them to transport all that you've done on CAPI 2, Power 9, or OpenCAPI. That's very important. So we have our power, okay, machine. We just need a very teeny, very simple libcxl library for CAPI connection. We need a very small library for Snap. We'll see how Snap is taking care to offer, so that's the Snap area. This is the hardware that the IBM is providing into an encrypted file, which will make the connection between your host memory and host to the FPGA, that's the FPGA side. It offers the job manager, a DMA, the control logic, the MMIO to access a very low-speed link, all registers that you need to have to control, and we can enter into the details offline if you need. We use, that's for hardware guys, we use some links to interconnect whatever DDR is I/O, whatever SSD you have as an I/O, whatever network as an I/O. It's installed because nobody has provided an open source network controller for the FPGA, so we need to rely on IPs. Okay? Then your software program that you are writing, you will see that you need to define what function you want to have into the FPGA. It can be described in C++ if you use this HLS conversion, or it can be directly described into logic. But less and less people are describing here because this is working very nicely. Okay? Let's go away from that. I think the best is to go on the example that we will demo. So, and the time is, somebody has a time?
Yeah, we have enough time. It's 2:15.
2:15, okay, very good. We will take a Hello World example that everybody knows Hello World. Good morning. So Hello World is used in this very simple case. We put a file into the memory, say T1 file, into the hardware hard disk. This file will be transferred to memory, and it contains capital letters and small letters. Okay. The goal of assume that you have a very extensive application whose job is to transform all these characters into small characters. So I've reduced your complexity into a very simple example for sure. What you need to do is take this file, put that in the host memory, that the application that does that, and the application is running a very small function that you have detected to be very time consuming. It's very time consuming, assume, to convert a character. It's an assumption for sure. This lower case, we will call that the software action. And you have in mind that this software action, you want to transform it into what will become an FPGA action. Once it's done, then you return the result into T2, okay? So the first step, and we will come back again, the first step that we require is that the software engineer is able to define what is the time-sucking application. What is the small function, like character translation, that is the hell into the computer, that is the hell into the GPU. That's, for example, the inference of a neural network. It's stupid calculations, but it takes time, lots of time. And you have in mind that maybe in FPGA, this time can be reduced, okay? So the first step is, from the main application that does all this, you need to extract, and that will be our first step, a function, and you need to define the boundary as we will see. My main function will be called snap hello world. Remember, we will use that on the computer. It works on an input, T1, and it provides an output. And by default, this doesn't exist because by default, you don't know about FPGA when you take the application. So a customer comes to us, it's okay. He doesn't know what CPU or FPGA is. But we will introduce a switch because later, what we want to achieve, and that's the goal of the demo, we will be able to run the application into a hardware described and working subroutine, which is, just for the demo, we say lowercase will be CPU and uppercase, the same function but uppercase, will be done in FPGA, okay? We want to transport this function into the FPGA. We want to remove that, and we want to go there. The FPGA needs to access to the host memory, and for that, we will use this CAPI link. I hope you are not lost. We talked about CAPI earlier, okay? It will make the modification on the file. It will return the file into the host memory, and then the application will be informed either by interruption or either by pulling. You have two options, very basic options. The application will be able to plot that to store that on the disk. Okay. What we need to have is a very simple switch. That's very basic, because we need to define whether we run in FPGA mode or CPU mode. We need to have a switch here to select whether this small action is run into CPU or is run into FPGA, okay? Once this switch is set up, the default mode will be run on FPGA, okay? And if you want to run on CPU, you will have to mention, I want to run on CPU. If you don't mention, it will try to run on FPGA. And this is a way to access new resources, as we said. So it's a little bit redundant. The card will offer you access to new things, a new DDR, networking, SSD, and so on, okay? So we won't go into all the details. For sure, it's very interesting, but we obviously have no time. We just explained in simple words all the exchange that are occurring between the action in FPGA and the software. So that's not the goal of this presentation. Just let's go into very brief details. Okay. So from the beginning, this is the application. So your main application, which will subtract, which will submit a specification to the FPGA. We need to define the address in and the address out. That's the minimum. So that's okay. We have a small structure that will be known by these two guys, and we want to limit the number of information we exchange because it goes through a very small, very low bandwidth MMIO channel. Okay. So when we call the application, when we call the action into the FPGA, we have reduced voluntarily, that's correct, to a very little number of bytes, the number we want to exchange. If you want to exchange more, put everything into the memory and give an address for that. Okay? Agree with the action that you have a protocol that say, okay, at this address in the memory, you will find all the necessary things that you require. So we have a very small exchange. It goes through the MMIO, for those who know this MMIO link, and we have these registers into the FPGA, which are known by the two things. We need to provide this to the MMIO, write the MMIO. Then the application will ask, like we do for a file or whatever, we need to allocate and find the card that we want to talk to. Is it available? Get an ID. We need to select the action that is present in the FPGA. The FPGA will say, hey, I have, so today, again, we support one action, but the structure is aimed at several actions. Say, hey, I have two actions, hello world and a specific mem copy. Which one do you want to use? I want to use the hello world, okay? So we get an action name, an action type. And once we have that, we will run this snap action. This is why we need a very small snap library into the processor side, okay? Because all these names needs to be understood. When we launch that, there will be a bunch of calculation from the FPGA standpoint, okay? We need to provide this register, this start the execution. The FPGA is doing things in the memory because it collects the text from the memory, manipulates it into the hardware, into the FPGA hardware, and return the text back to memory, okay? Important thing that we have written here, by the time the FPGA is computing, you don't need to wait, that's the goal. We are offloading the activity. So you give a very small bunch of instructions, what are the address, what I expect from you, where data located. You give the job to the FPGA, and then you can do something else. At this time, the FPGA can say, I'm finished. It can generate an iteration. It can write a bit into the register section saying, I'm finished, but I have still some more job to do. I finished the first part. But you can continue like I'm waiting for a new video to come. I'm ready to uncompress, but no video for the moment. So you say 0, no video, and first one is ready. Then when the application has time, it can take care of what's happening. For example, the FPGA can uncompress all video coming on its Ethernet channel and saying, is there activity on the video? Yes, no. So you get a bunch of videos, and all the videos that have no activity, you just throw them away to garbage can. And sometimes one is moving. The thief is entering into the shop and says, this video is important. So you say, you raise one flag into your register and say, I've got one video with activity. And whenever the application wants to get this video, it checks, it polls, and say, oh, you got a video with moving activity inside, very good. But the other ones, I know you've put them to garbage can, but this one, I told you to put that in the memory. Nothing to do, the application goes into memory and gets the video for further analysis. Okay? All right, so we have been through the main step. Okay, at the end, we need to release the action, release the card, and free the two memory buffer that we have reserved for the two files. Okay? So we have tried to make your mind structure to discover this technology and to have our minds, not yours, but our minds, to describe 3 steps. This way in the demo we know where we are. The first step we already said, we need to define what is the action that can be externalized, and we need to do some software activity to make sure that we know the boundary of this action, and this boundary will be the exact same boundary as the one that we will use for the FPGA. That is, in our case, input register where the data are located, output register where the application expects the return of the data to be located, and a bunch of register like I want to be pulled, I want to be interrupted, any very little, very basic information into this register. The first command, when you have made this extraction, that means from your main application you have extracted what you want to externalize later on, you just make, and this will make the software. And you want to make sure that this is working by using a virtual register, okay, that you will hopefully at the end have in the FPGA. The second step is, so first step you say snap config is CPU because we have introduced a switch. So we want to run in CPU because remember by default we run in FPGA. Snap hello world, and you work on these 2 files. This should work, okay? When you create your application, it should work. First step, no FPGA at this step. Second step, we don't need hardware, and that's very good because you will see on the demonstration that we can do a simulation. We will see why. We emulate the hardware behavior, including all the PCI exchanges. That is, you are really at the maximum, you have a tight complicity with hardware. The hardware is not existing, but all the links to the power is emulated. And that's a huge work, I can tell you. This simulation engine is a marvel. It's really nice. So you will submit as if you had an FPGA into a simulator. We are using the Xilinx simulator. We can also use Cadence simulators or any simulator you like. And this simulator will accept, will talk to the virtual CAPI link, okay? The simulator will by itself get in the actual memory of your server. And the last sentence I have said, I can tell you for hardware guys, I'll repeat the sentence, it's magic. The simulator will get the actual file into the actual host memory. Manipulates it, for sure it takes a long time because it's a simulation, and then it will return the result into the host memory at the location that your application has described. That seems very simple when we say that, but let's say more than 10 years ago it could not have been guessed that we could do that on power technology. And once you are happy, so we say here that the test bench is not required. Your application is your test bench. You don't need to duplicate on the side. What if I had a CAPI link? What if I have a video? Okay, provide a very basic header of the video, and this uncompressor will take the header of the video and will tell you the video is not a nice format. Okay, it's very simple. Don't use hundreds of megabytes to supply the simulator. It makes no sense. But for understanding all the connections between your action and the application, it's very nice. And once you are happy, you can go into the FPGA. This takes few minutes to be built, the simulation engine. To provide the actual file into the FPGA, it can take between 30 and few hours, depending on the complexity of your action. Okay? Then you go into Power 8 or Power 9 server, and then you deploy. Notice that here there is a constraint that comes from Xilinx, which is our partner for FPGA. It's the best partner today since Altera has been acquired by Xilinx, I can't say what, no, I'm sorry, by Intel. And I was just joking. So we can work with, for sure, we can work with Intel FPGAs. But the thing is that we have developed everything under Xilinx because it's very nice, and their HLS tool is very nice. And also the capability to work with power is built in. It's very nice today because the work has been done, so it's working nicely. All right, so the point I wanted to come back to it is that the Xilinx tool, the Xilinx is the provider of this part, the FPGA. They don't want to provide that to be compiled on Power. Otherwise, we could do everything on Power. So we need to develop on x86 because their tool is compatible with Linux or Windows, but on x86. And at the end, we need to transport our files on the Power server. Okay?
So is it RTL simulation? The simulation you're mentioning is RTL simulation?
Yes. High level, behavioral.
Well, there are RTL simulation and there is system C simulation. So the behavior which you're saying should be a system C simulation, which is quite fast. If you're saying RTL simulation, it is actually quite slow.
Yes, it is slow. It is slow.
It's very slow,
Yes.
actually. And another question.
But what you want to obviously to simulate is mainly the link.
Mhm.
You don't care about simulating your activity.
Yeah,
because
of
this
course.
you can run
Right,
fast.
finally it will run fast,
Yes.
of course.
But what you want to simulate is all the access, and this is what is nice.
Okay.
Okay, we don't want.
And you're leaving the logic part dependent upon the HLS tool.
You can do development of RTL by yourself.
Yeah.
Snap is the same. At the top of Snap, but it goes into details. We have this HLS. If HLS is going fine, then we go to Snap. If HLS is not going fine, then we say, hey, you have to go back. Like in Monopoly, you go back to jail. Okay? And come back when you're free. All right.
What is the street price?
I'm sorry, we have the demo to run, so maybe we can. Very quick question. I'm
What
sorry.
is the street price of the license for exciting?
I don't know. I don't know because I'm working in lab
The
and.
tools, right now, I mean, they're available, it's packaged in a completely on-demand fashion in our platform, but they do license them, I think. I don't know what the...
Few thousands a year?
Yeah.
Few thousands a year
Yeah,
for,
yeah.
for what you
Yeah.
need here. But we'll see that with Nimbix it's included. So the Snap ecosystem is managing all these companies. Vivado is a tool from Xilinx that is providing the FPGA Infinite. These guys are providing cards, so they are being acquired, so it's in Molex. We have Alpha and Mellanox and Reflex also. Four card providers, which we have acquaintance with, so we are working with them. We have in the middle the power technology, and so between software, GitHub is hosting all the tools. So between us, IBM, the software, and the card provider, everything is embedded into this Nimbix tool that we demo. Everything is working very nicely. Okay, and you can test all what I will demo for only 36 pence an hour for the two first steps, x86 development. And when you deploy, it just costs you $3 an hour. So that's, I think, a very, very good price. Thanks, guys. Okay, so let's go to the demonstration because I've taken things from a more complete presentation with a demo. Okay, so now we go, that would be interesting. It's better to be in front of the computer, so I hope this one is working. Okay, this one here. All right. Doesn't want to work. Okay. Sit here. Can I sit here? It's okay?
Yes.
All right. So let's go here. All right. So I will use my account because it's easier.
If you like, you can sit in the chair. The cable's very long.
Or for the moment it's okay because
Okay.
I need to see.
Oh, okay.
Okay, so I won't go through the steps of saying Nimbix, hey, you don't know me, this is my email, this is my address, this is my magic blue card. So please give me an account and I'm ready to pay for working with this, not only with our tool. You will see there are lots of tools. So they provided to me an account Actually, it's not my magic card. It's the blue company card that is IBM is paying for my test. So they can rely on this magic card. Okay. When you come here, you have a bunch of. We cannot see all of them. That's not the goal. But you see ANSYS, you see POWER. So if we say IBM, I guess we get all the icons from us. Okay, so you see from IBM, maybe it's not exhaustive, but we have POWER tools, we have TensorFlow examples, we have CUDA examples working on Power. And forget about these locked icons, these are for development. So it's for CAPI SNAP, we have 3 icons that are hosted by their system. Okay, so let's go to CAPI. Okay, and forget about this lock. So we have mainly three icons. The main one is for step 1. Okay, so I will open a desktop. I just recall the slide we have seen already, just for you to have in mind what we intend to do. We intend to take an application and to put a specific part of this application into the FPGA, like action 1, action 2, and we will use a specific library, a specific snap library. We will use a specific hardware that IBM is providing in an encrypted file. The snap will provide all the connections for you, and we won't use the DDR on our example, because our example is just using the logic to catch the file. Remember this file that we want to change the cast? We take the file, modify, and put the file back. So we don't use the IOs in our example. Okay? We say I want to build a machine. The basic machine is enough. You can select that you want the SSH if you want to play with your terminal from your home, or from your company. You have a license to agree with. So believe me, I've read everything and I totally agree. Why are you smiling?
It's a 1,000-page license from Zion.
I've read them.
So when does page 800 start?
I had a translation issue on page 52. Okay, and then we wait for the main dashboard to build my machine. By experience, they say click here to connect. My experience says wait for the blue stuff to come, and then you'll get the screen directly. If you click now, then you have to refresh until the machine is ready. So now, what is going on is that at IBM, we have prepared a set of Docker file to offer here on their machine the system that includes the Vivado tool. Vivado is being the tool used by Xilinx to prepare this hardware stuff. So this is how do we say when we build tissue, we have a machine, sewing machine? The sewing machine, okay? So behind there is a sewing machine, okay? Right? So I can open it. And behind the scene, we have prepared the access to the tools.
Make the zoom smaller so they can see it. Just
Which one? This
that
one?
one, yeah. Click that. Now it's 100.
Okay. So basically, we want to open this terminal. It's I think it's okay. Can you read? Can you read what's going on? Maybe not. Okay.
Deploy to power.
So what we have prepared is few files. One file will set up the environment. So let's have a look at it right now. Okay, this file is really how should I say? We try to have this experience the same as the one you could have in your lab. So what we have imagined is that you don't know anything about FPGA and you are scared because your colleague said, "Oh my goodness, FPGA is a nightmare." I said, "No, I attended a presentation at academic workshop on OpenPOWER, and the guy said it's not that nightmare. It's okay." So I want to try. No, you want to install students to install the Xilinx tool and so on. It's a nightmare. I said, no. He showed me all the tools are installed here. Okay, but we don't want to hide. We don't want to say everything is magic. So at each step, I will tell you what is available already at Nimbix that you have to do at home. At home or in your lab, you will have to set up all the gliding stools with the proper level of release, matching the hardware you have. So here, in this case, Nimbix is offering 2 cards at the end, one alpha data card and one LaTeX card. Is offering a P8 machine, okay? And we have set up this Xilinx tool to work on these cards nicely for you, okay? At home, you might encounter troubles with Xilinx not supporting this FPGA that your friend has provided to you and so on. Here, everything is set up so the goal is that you experience the technology, and then you come to us if you have specific needs. So if I say which Vivado, just to show you that this has been installed on the Docker machine, we are using this earlier 2018.1 binary Vivado. So Vivado is working. I can run it on the machine. This is why it took some time at the fabrication. We need to build the Docker. We need to be on the right system. We work only today on bare metal. So we are at the end in the power when we deploy. Okay. So we need to have this setup environment. Now what we have built this file and this file. Okay. So the quick start guide is me in electronic format. Okay. So you don't have me, and your friend doesn't believe me, doesn't believe you. Say go and follow this guide. And with this guide, that we won't go through because it's part of my presentation, and the card we support, and the things we have spoken about. Okay. We won't go into details, but we explain a lot of what's going on. Okay. We explain where to request your account. We explain where to launch your machine. Click here to connect and so on. What you have in your desktop. Okay. So we are at this level. So no need for you to go into this file, but this is the head file that we want you to go through step by step. And here, that's not for the guy who never, or the people, guy or woman, who never look at the documentation. So you receive the printer, you receive your snap, you have a nice access to Nimbix, the cost is reasonable, and you want to play. But okay, you want to play, you can copy-paste stupidly these things. But it's better to understand what you're doing, because it's technology, okay? Okay, so we have just for us for testing, it's very easy. We have just copied and pasted the steps that we want you to experiment. The first step is to go and clone. This is cloning the HTTPS GitHub OpenPOWER snap. So we are connecting the snap into the machine. Okay, and this should be in the center mouse. Okay, that's demo effect. You know demo effect? Okay, I think I am experimenting the demo. Oh, I invalidated the. Okay. Let me go back to Lenovo. Control panel. For some reason, the center button is working only on my search pad. So do you see mouse? Mouse. Oh my God, this mouse here it is.
You want a mouse?
No. Oh, yes, very good. Oh, you saved me. Okay, now I can remove this one because I don't have any more.
For most there, but you never most here.
The other one should work, but sometimes it doesn't work. Okay, just enable this one for the moment. It takes time to get the. Okay, so we are cloning the directory, right? And we are entering it. Just before we enter it, remember that, okay, we showed, hold on 1 second. I go to snap, okay? So this is the step here. Oh my goodness. Right. Okay. So, okay. Git clone, get the snap. CD snap, and once you are snap, we propose you to check out a cloud branch. This is because we had troubles at the beginning. One, people are developing, something was working in Nimbix, and then they developed something, and then it's not working anymore, so it was boring. So we defined a release of snap that makes sure that you are not bothered with development. Today, we don't need that because the latest release is working. So I just go to snap, I am in, okay? And then the only thing I need to do is copy the environment file, and we'll see what's inside, into the directory where we work. So let's have a look at what it is. No magic here. We define 3 basic standard directory. Export PSLSC. PSLSC is a simulation engine. PSL is the processor service layer. Remember this blue logic that makes sure IBM is making sure that your FPGA is or your any CAPI device will use this hardware is working fine with power processor. So when we want to simulate that, we need a simulation engine, and it has been already installed on your machine in /home/Nimbix your account PSLSC. This is just to save you time to download this one. So install Vivado tools. Provide the PSLSC, provide a snap, okay? Get the file. The second file is a Nimbix specific location where all the production, the ultimate binary, at the end, what we want to do is get a binary file that we will put in a dummy flash into the dummy card, okay? So that when the dummy card with a dummy ASIC, which doesn't know anything, it's just a sea of gate, when it wakes up, it will say, what do I have to do? Oh, I know one thing, where to get my information. It goes into the flash, get the binary file that we will put in this directory, okay? And then it will wake up like, oh, I'm a video uncompressor. Oh, I am action 1, action 2, action 3. Oh, I am a case transformer for the hello world example, okay? So ultimately, the file that we will provide on the machine will be located here. It's a snap directory because we created it. The date, and we certainly add the time because sometime in the day you fabricate several images. And PSLDCP is where is located this hardware logic for the specific card. For P8, I don't enter into details, it depends on the card. For P9, we wanted to get rid of the card, so we provide just the minimum hardware, whatever the card is connected to. But the counterpart of that is that you need to provide the description of your card somewhere. Okay? So there are 2 directories with a variable FPGA card, one for alpha data, one for Nalatech, because we have 2 cards on the system. Okay? Provided these 3 information, Snap can begin. The first thing we want to do is make snap config. That makes sense. We want you to configure what you want to do at the end. Make snap config. It downloads an open source menu that you can edit by yourself. Everything is open source. It has advantages and disadvantages. So let's see the advantages that it can select for you. You can select a card. So first menu, you have a bunch of cards, okay, including the latest one, CAPI 2. Okay, we have 4 CAPI 2 cards that we can run today, and 4 CAPI 1 cards. Okay, these 2 first cards are the ones that Nimbix is supporting. If you select another one, you won't be able to deploy on them. These are the cards from our Chinese colleague. So for Chinese people, they can work with these Chinese available cards, very low-cost cards. And we will select, so for example, the Nalatech. This one has an SSD on board. So when I select it, I can enable the driver that will be installed into the FPGA by the Snap tool for you to access seamlessly the DDR on the card. The FPGA can access the DDR on the card to manipulate a file. It can take a bunch of things into the host memory, manipulate it into the DDR, or he can collect video from the internet, put that into his DDR, not to worry the processor memory, work on it, put to garbage can what he has to put to garbage can, and then at the end, if something is interesting, he can copy that to the host memory. So when you see that, it's because you have this SSD on the card. The simple menu allows us to remove this selection. If I select a card that doesn't have the NVMe, the NVMe disappears. And this is very simply coded, so it was a trade-off. Because we are open source, we also want to play the open source game. We don't want to have a huge IBM specific tool, configurator, terminator, or whatever, you know, all these things. So the advantage is that it's very simple to program. We will select an HLS hello world. This is the example. Well, you will see HDL and HLS. HDL are coded directly in RTL, this language of gate description, where HLS had this conversion on top of Snap, which allow you to describe this case transformation into RTL and hopefully put that in your car. So basically, I'm mainly working with my colleague Bruno in France on the HLS things. The HDL is less and less used because people are more and more using HLS. I have an example of scatter gather where our colleague in China, and that's a small, we can talk that a little bit later if we have time. It's interesting for the comparison. I let the simulator, the Xilinx one by default, because it's included, no tools to add. I want a cloud build because I'm working on Nimbix. Okay, and this is described in the guide, so I say exit, I save, and it will just prepare the Snap environment file that I've provided with the three, remember these three variables? It will add into this file whatever it needs to work. So we still have these three files that I have provided at the top of the session. And he has said, I export a PSL version 8 for one time. I'm very happy because PSL version 8 is for Power 8, yeah. PSL version 9 is Power 9, yeah. What we will use for OpenCAPI, I don't know, because it's a 9B or, okay, but it's very nice because you can check that it's a Power 8 board. The action we have selected is located into the snap root, this variable that we use, into the action. Let's have into the action, we have all the HLS examples. So in this HLS hello world, you have all the software and hardware description that we will use as an input for you to understand exactly what we have written, how we make memory access. It's all detailed and commented. And if something is not commented enough, please tell us, and we will add the comments that you were missing. Or if something is not clear for you, please come back to us. It's open source, so make suggestions. We can make errors. So please come back and comment. Time limit, that's for hardware guys. We said we had the complexity. We cannot prevent hardware guys to take some of the Airbus panel and say, hey, take this one here. So we are in the glider, say, hey, give me this, I want to check that. And it's a trade-off because this will make sure that the hardware will work, and we need some variables to make sure that we have obtained a result that makes sense. Okay? So now we have done that. I can rely on this one because it's a good memo. The first thing I need to do, or I should have done that earlier, but it's okay. I should make software. It's because the software guy have put some dynamic libraries. Don't ask me what it is because I'm not software. But it's a pain for us because if we don't build that at the top, when we go into the branches, we cannot make the software because the software relies on Snap libraries which are dynamically linked. So we need to provide that for things to work nicely. It's another step that we did not have to do earlier. But apparently it's better for software guys, so I believe them, it's okay. We go to the configurator, we select the KU3, we have selected the second card, KU3. We select the HLS hello world, we select cloud build, that's what we have done. Okay? So now we go a little bit further. We have made the snap config step. So now we will make a first compilation. Okay? I will go into the directory, or let me make a step here, and say cd hello world, ll. I can also check the directory from here. OpenCAPI. Okay, what is this one? Oh, this one is PSLSC. So this is the GitHub for the Power Service Layer Simulation Engine. Okay, and I wanted you to see the snap that we have downloaded. So what we have downloaded at the first step is documented here. Okay, so you have all the information of what you need to install on your machine, what card you can use, which computer. We have also here the structure, and we see that in action, the directory action, we have all the provided examples, and it's going higher and higher. The more we work, the more people are okay to provide their work into the GitHub. Not everybody is inclined for that. And we are happy because there is a neural network that we have been authorized to publish here that will come soon from the Zurich research from IBM. So you see that inside an HLS hello world where we have several directories. The first one is a software directory, which contains your main application, remember, the one that gets the file and provide that to the action, whether it is CPU or FPGA. And this is the action, lowercase, this is the software action, okay? With exactly the minimum. So you can go into this file. We won't go into the detail now because we don't have time. And here, hardware is prepared for you, the CPP description of exactly what will enter into the HLS. I cannot go into details of optimization and so on, but for all this, when you're back in your lab, please go and have a look, spend some time. You have a documentation directory here for each action. We try to have a PDF describing what I'm telling you, and also in the main structure, here we have a document, a snap. Okay, we go to snap, doc. We have several files that we want you to read. The quick guide on a general environment is the same guide as the one that I have showed you, but the guide we showed you is specific to Nimbix at the top. For the rest is the same. And this one is for you at home, what you need to do on your lab, what you need to do. You want to check how to debug an issue. Most of the time, the question you have for us, we already had it. So anytime we have a new question, we put this one here into debugging new issue, and it's a collection of known traps in which we fall. How to create a new action when you're happy with hello world, you want to create your own. So how you do that? How data are managed? How do we change data so you can exactly understand in details what's going on? And hopefully how to port and optimize. That's for HLS, to ease the transformation process, because not everything can be converted. For example, very small detail, if you have a clock access to the host memory, the FPGA doesn't know the clock of the host system. So anything that is clock related needs to be reworked, rethink, okay? We cannot take a clock dependent action and put that in an FPGA. The FPGA doesn't have the time of the system, okay? Or you need to write a routine for that. All right, so let's come back here, because time is running quickly, and we will be running out of time.
We have 20 more minutes.
Yes, but we have many things to do, so...
Okay.
This is where I'm scared, because I talk too much. Oh, maybe I have closed the window. Okay, I'm relogging. Okay, I reconnect to my session. I hope this will work. So you see, when you have your session, it's just aligned with your default Nimbix user and password, which is for your session. That's very nice, because you can share that with a colleague, with your customer, with your partner, and say, where are you in trouble? Okay, give me your pointer. So sometimes it seems that we have a local, my colleague said that.
Refresh again.
Yes.
It's collective.
Yes, but it said there is an issue. Okay, here we are.
We have a strange issue with the network inside this office sometimes. Sorry.
Okay. So I'm going into the software. Remember, there are 3 files, the application, and this is the first step, okay? And I say make. I just build these 3 files, and then I want to test that I've prepared things nicely. I need to select CPU mode, because we are in Snap, so we need to mention that we stay on CPU. I will, sorry. Okay. Check the result before CPU. Okay. Okay, this is the file. This is where I prepared the file. I just copy this to T1. Okay. All right. Okay, good. So I have my file with capital I, okay, and capital Snap. Now I run. So nothing magic here. It's just pure software. I run the CPU mode. I fabricate. Oh, it will tell me that it took 9 microseconds. Remember that? 9 microseconds. We will compare with hardware, because we don't cheat, no optimization, and we expect hardware to be to be what it is. And we take a file at D8-1000, D8-2000 for the return at the host address. You don't have to take care about addresses. You have an address in your application, the FPGA can read it. And that's very nice. Power 8, Power 9, Power 900. And we have written 50 bytes into T2. We say more/TMP/T2. And magic, the software works fine. All is small letters. Okay? So we just check that everything is working nicely. Now, what we want to do is come back to Snap, and we will make sim. So CD Snap, whatever you want. And now I do make sim. Make sim is doing two things. So first one was a make, second one is make sim. If you type make, you have the list of the options. Make sims will make model, and make model is preparing the minimum hardware for the simulation to work. Okay? We have no DDR in our example, so it will not prepare, let's say, not a dummy, but a basic DDR driver, no need. It will just build whatever it needs for the FPGA in simulation to talk to the memory, to talk to the hardware, to the software, to whatever it needs, but pure simulation. So it generates things. It generates, so see, for example, FPGA PSL to FPGA connection. The FPGA is connecting, FPGA side that is for the user is connecting to the PSL, the blue logic that talks to the computer. It creates the MMIO where we store the information for the register. It creates a top file, that's for hardware engineer, the top description of the complete FPGA, including all the pins and so on. He put all the wrappers, and that's nice because every time he put that, he has a source file, and he says, do I have a DDR memory? No, skip. Do I have an NVMe? No, skip. Ethernet? No, skip. Okay, I have just basic. Okay, I need to cut that. This I remove, this I connect. And all this is done in a few minutes. He gets all the FIFO model because he's using FIFO. He's connecting everything. It takes about 3 minutes for this very basic example. And once it's done, make model, he adds a make sim at the end, which is launching the simulation. It's just easier for demonstration. So when he's ready with all the PSLSC connection, making the model, export simulation, okay, he will run and we will get a small window so I can prepare the command I will launch. And we will see in this window that the first thing we need to do is snap main. It means make sure that the power processor and the application has the minimum requirements from the card. Who are you, which ID, and what action do you know? So snap main is a very basic command that we will launch into the command window. All right? Then we will do exactly the same. The T1 is already existing, I don't need to rewrite it. And this time I will not mention that I want CPU because I want FPGA. Everybody is following me? Okay? Snap hello world, -v just to get some information. Insert input file, output file in T3, and then I will check T1 and T3. In the simulation I can run again the CPU mode, because I'm simulation, I want to compare, I want to trick things and so on, to tune. Okay, the simulation is, now the simulation is running. So I'm in a new terminal. We could have that here, but it mixes up the simulation results and what you want. So for an experience, it's better to have a new window. It could be a simple terminal. The bad thing about that is that you need X11 to run. So if you are in SSH, you need to be SSH with X11 emulator, okay, or being on Linux. So we can just snap main, which is the exact same command that we will run in hardware. Snap main is very interesting because it says I have an ID card 0. In simulation, we have only one ID. If you are in hardware, you have 0, 1. On D8, I think we have 2 CAPI cards. It says it's an ADKU3, so you know which card you have selected. It says no NVMe on the card. No RAM has been hooked up. There is RAM on the card, but we said we don't need the RAM because it's a hello world. We unselected the RAM. In the main menu, by selecting HLS hello world, in the background, we said we don't need the DRAM for this basic example. We know exactly that it has been built from the release we have made yesterday or 2 days ago, 1.5.1 from Snap, and we have a distance of 0. Nobody has pushed anything since this release. And this is the Git reference that I used to prepare this model. So we know exactly where we are. It's built today at 9 o'clock, because the time of the machine is 9 o'clock, I don't know why. And it contains an action, which this number. We have reserved 10144 for IBM. So this is the 8th action, version number 22 of HLS Hello World. And the system is ready to answer. So now I can play exactly. So you have seen that the test bench is really basic. The T1 is existing, so I can directly run that. I launch the simulation. For sure, it doesn't take 9 microseconds. Okay. And it takes, so micro, milli, it takes 2 seconds to simulate what we make for the character by character check, is it high or low, and make it high in hardware, okay? And then at the end, okay, we get a T3 file, which is the output, T3, T1, same input, different output, we get all capital letters, okay? Now the good thing is, okay, we can rerun that in CPU mode, it works, just to save time. I will just exit the simulator. And one nice thing here is that, I'm sorry, I'm a hardware guy. I will just take 2-3 minutes just for my own pleasure, because it's so funny. And I beg your pardon to the software people. Okay, I will go into hardware, into scene, okay, and we have prepared this X-scene trace, which if I launch it, and again, I'm very sorry for this. You'll see it's very hopeful for software guy. This is chronograms. So he's launching the Vivado tool, and he should be opening. He should be opening
The clock cycle.
Yes, yes, yes. Oh, you know what we can do is just, I have prepared this one. I have prepared this one on my machine, so this way we save time for the configuration. And also the size is not that big. But you see here, we get all the okay, let me open this window. Where is the mouse? You see it? Oh, okay, the windows are reversed. Okay, so I need to go there. Okay, I've prepared here. If you select data, so it is the same calculation on the same example, but on my computer, because I've prepared that earlier this morning, early afternoons. You see that this is the exchange of the chain. Hello world, this is my first CAPI experience, okay? And we can check at each level what is transferred byte per byte. So for debug, when you are debugging IOs, I can tell you, you save lots of time. If you have a problem with big endian, little endian, if you have a problem with ordering, whether your header is with MSB or LSB first, it's really a nightmare. So you see, for example, here, in this case, I read in the other side. So letters are in the other side. FIRST first, CAPI, CAPI, SNAP, okay, experience. So I can check that my hardware is queuing from the other side. It's getting the characters by some order. So I can check everything. End of the bracket, I'm very sorry for I hope you pardon me.
You could translate it as in hardware time.
Sorry?
Now you could tell us the hardware time.
Yeah, exactly. We know exactly how long, how many cycles. So when we say clock in hardware, we speak about the FPGA clock, not to be confused with the
real-time clock.
With the real-time clock. Okay,
Yeah.
It's totally different. Okay, and in hardware we can have several clock domains. When we say that to software, they say no.
Let's not get into CDCs.
It gets crazy. So clock is a source of misunderstanding between when we are speaking about this environment which is making a bridge between two domains. But knowing that we had, we can check that, for example, we have an information which is action start. Action start, when we do a snap main, the action is solicited because the action needs to reply whatever it has in its system. So we'll see a pulse action start corresponding to the snap main. Then it took me a few seconds before I typed so if nothing happens, I think the simulator is not counting the time because it's useless. But then we will see an API start for all the time that the chain of character is analyzed, and once it's finished, API stop, application stop, okay? So I can measure exactly this time, and because I have the clock here at the top somewhere, I can measure exactly how long it takes in the hardware. This will not take into account the actual CAPI link timings, but what Lance, our colleague, has done, and I can tell you this is very, very nice job, the CAPI modelization is also making the packets in different orders. And you can select that I want the packet in the same order because it's easier when you debug. And then when it's working, you say, okay, now change the order of the packets and get the numbers and so on. So you can really debug even the CAPI link a little bit. Not in hardware, but the overall behavior of your CAPI link. Okay, I can talk hours about that, and the time is running, so we won't have time. Okay.
6 more minutes.
All right, no, this is not the one. This is the one. Okay, good. Oh, I wanted to close this window, but okay, good. I close this one. One. Oh, okay. So now what we have done is we assume that we have prepared the file, understood what's inside. We have no time to go inside the details. The simulation is working as expected. You have seen that these characters are capital. So we have been through the simulator. Oh, we forgot to check how long it took. Yes, we said 2 seconds. Okay, very good. So it took a longer time. And this is real-time clock time. The 2 seconds is me as a Power 8. I submitted the job to this bloody and stupid simulator, and it took him 2 seconds. So it's a huge amount of time, but it's a simulation. Okay, it's a time from the power. At the beginning, when I entered this domain, I said to my colleague, "Hey, why is it 2 seconds? 2 seconds? Because it's not the time of the simulator; it's the time of the processor." Okay, this is where the clocking is sometimes misleading. Now the simulation is running. So the next step, we exit the simulation. We make image. Make image, I can launch the process. And it will take, I'm not in the good directory. I need to be in the snap directory. And launch make image. The beginning will be exactly the same. It will scan the configuration file, check HLS support, yes. No RAM, no VRAM, no NVMe, no debug. Okay, simulator, yes, it's a XSIM simulator. DCP rules, remember this is where I want it to put the binary file at the end. And what our colleagues has done is that when we are in cloud mode, that is not on your own machine, to respect the hardware that Nimbix is hosting, they have defined, I don't know what is the history of that, but when we prepare a binary file, we also prepare a signature file which goes with it, making sure that Nimbix is only hosting files that they have prepared on their hardware under our control.
Can I comment on that?
Please.
Because I can explain. So the reason is that this method is full configuration of the FPGA. So we want to make sure that if there's a mistake in the bit stream, that it doesn't actually cause the FPGA to have to be reset with JTAG, to where somebody would have to go to the data center and do it. So in partial reconfiguration, that's usually not an issue. But in this, we built this specifically to verify that the images are good before they're actually perfect. So, and it's worked,
Yes,
quite well.
quite well, exactly. So it's a specific, very, very teeny difference. When we make the image, we make an image in cloud mode, means that, as I said, we have a specific process, very specific process. This doesn't prevent you to prepare a standard image, take this image and run it on your hardware. Okay, right?
Well, you can download the image and run it wherever you want. Right?
Yes, I've done that, so it's okay.
Yeah, exactly.
Yes.
It's just if you're running it in our platform, we want to make sure it's verified.
Yes, but if you run on yours, then you can unselect the cloud mode that we have selected in the early process, You will not be in partial reconfiguration. You won't get this signature file, but you will only be able to develop on any power machine, but not theirs. Okay? Or unless you come and
If you come with a JTAG cable. And
no. The actual image we can load it on your
Yeah,
machine.
that's right.
By,
Right, yes.
by link,
Yes.
by fast link.
Yes.
Okay. So this we won't wait. It will take about 30, and the machines are fast enough. It can be
This is on
25.
that really small machine, right?
Yeah, you're running it on I think you're running on a small Intel class machine.
It's running fast.
Yeah.
For me, it's okay.
Okay.
Yeah.
It's 25, 30 minutes for a
It's,
hardware
it's,
guy.
it's
It's
still,
okay.
it's much faster than a local machine, but it's a very
Yes.
small portion.
Yes,
of it.
exactly. So we won't wait, and in the meantime, because time is a resource that we don't have unlimited. So it's a new window, or let's take this one, Jarvis. I come back into my environment. Oh, okay. Before I deploy, assume that we have waited 30 minutes. We get this image into the directory that was mentioned. So I know where it is. I can deploy. I have a script, and automatically it will call a Power 8 machine in their lab and program the card with my binary and launch a machine with this card program. Before I do this, I need to make sure that the machine is available. So we have currently 2 machines hosting several cards, or no, 2 types of machine, okay, 2 types of P8. Some P8 containing alpha data card, the one we're using, and some P8 containing Nullitech. We can check that if all machines are used, it's red. If all machines are available, or several machines are available, it's green. And orange means there is a machine contention. So be careful, you might not have the machine. Okay. So we are in green state, KU3. That means it makes sense. I can play with this machine. So I go back to my account. Okay, this is the one. Okay, oh, I should have selected. It's selected. No. I should have selected that to avoid clicking every time on my account. And then remember there were one thing. This is my window, a summary of make image. This is the machine with the make image I typed. And once it creates the image, the long process is run on a separate machine. That's very interesting because, say we are Friday, and I don't want to be bothered because I want to go on weekend, so I launch make image. I make sure this guy is running. I can close this machine, so I reduce my cost, which is not that big, but it's a weekend, so I don't want to pay for the weekend. And this one, if it fails, it will close anyway, whether it succeeds or fails. So Monday I come back, I go check the history. Yes, my image is ready, new week, new problems, okay.
Yeah, so from a sort of cloud utilization perspective, that's a batch mode process, as if you were submitting it on your supercomputer. So when it's done, the resources are freed up, you're not paying for them anymore. So unlike in AWS, where you have to go in and shut down the instances, that automatically shuts down, and we have a lot of workflows of that type on our system, not just this one. It's a really good sort of cross-optimization for cloud.
Well, this one is your development machine. If you close it, you close your Windows and so on. So they offer you, again, I'm very happy with what they offer. They offer you a directory where you can work and put your data. And if you are a registered user with Magic Blue Card, then this history is maintained. And this is what I will use. So I will call a deploy. So you see we have 3 images. Okay. 3 images: the development, the batch, and the deploy for the Power 8. So assume we are Monday. This process has built things I'm happy with. I call a P8 machine. I go back into my directory, which is maintained, although I have closed all my development and batch and so on. Everything is closed. I come back on Monday. So no building during the weekend, apart from the batch I have launched, which has ended some time. I go back to, I prepared files like 2 weeks ago for TQ hello. I catch this file. Because of this signature I need to provide, and we will work on having only one menu hit to simplify that. I provide the signature associated file, and I submit. Okay. It says there is a timer, so we are considering not having the timer for the paying users, because sometimes people need more than 1 hour to work. It creates a Power 8 instance, loading the binary I have provided, which I have prepared 2 weeks ago, okay, or maybe yesterday, I don't know. I don't know which one it is. And once it's working, okay. So in the meantime, while the machine is running, I can show you on a machine in Montpellier, that is a machine that we have in our own lab. So Brahma. I can show you another, and this will conclude the demo. Okay, this is a card I automatically launch at Logon. Which card do I have on my system? So I have 2 cards. This French card that we have been developing, and the N250SP, which is a very well-known IBM, almost IBM. It was about to be an IBM reference. So we have two cards working. If I say snap maint, okay, I have an alias snap maint, because it's long to type. I just say maint, okay. So maint, I think on this machine I need to be sudo. So sudo is done already, so it will ask for my, so maint will show me what is in the first card. So in the first card there is a latency evaluation example, I will show you. And on the snap maint minus C1, okay, I have an HS name copy, all right? So I can run test. I think I run them this morning, so I can, okay. So on C1, I will launch a test which is provided into the examples. This is aimed at being run in automated mode to make sure that when we modify the GitHub, we don't kill the snap. So this will show the throughput to the DDR. Or sudo. Okay, and you see that the throughput, that's on the P9, CAPI 2, 12.5, 14.2, 14.7, 13.4, they are all about the same. This is copying from host to FPGA, host memory to FPGA, 500 megahertz from host to FPGA, back and forth, and this is local copy, that is to the local DDR. And you see that the FPGA sees the same speed to copy. Everything is quiet around. Okay, no other bothering actions running, no other applications. But it's as fast to copy in the local DDR on the card as it is to access to the host memory. So if you remember the card we have seen at the beginning, Alpha Data is making a card with OpenCAPI, and they don't put DDR on the card because they estimate that the access to the host memory is fast enough to provide good access. So it's an example that you can run on your card to make sure that you have the right performances. And let's finish with this one.
Try the refreshing. So the reason why it took so long to get the screenshot is because it actually programmed the FPGA when it launched. So that's done automatically and using the verified signature.
But there the FPGA is programmed already, so I think it's a question of accessing.
Yeah, this is the other issue.
Yes, this is the other local issue. So the machine is only 3 or 4 minutes. Okay, there we are.
Yeah, but the point is that if, for example, somebody comes along and wants to use the same machine with a completely different bit stream, then the system will reconfigure it on the fly using our technology. So it's what we call reconfigurable cloud computing. It's actually what Steve invented years ago.
Okay, so we'll git clone because we are in a new machine. I'm sorry for the delay. Do I skip the pause or do I keep the timing of the next presenter? I'm a little bit offline.
Yeah, complete.
Okay,
Yeah,
so we get the branch, we source the path and so on, and then we make the software exactly the same things we did earlier, and we will do this snap find card. So we make the software the same way we did earlier, okay? And doing the snap find card. We didn't do that in simulation because in simulation there is no card. actual card. So we have skipped this step. But remember the things I have showed you. I had 2 cards. In this machine, I have 1 card in position 0. It's this revision of PSL and so on. It doesn't tell me, as comment, it doesn't tell me what action is inside. I need to run this snap mate to know that there is an HLS hello world dated node file, because I took a node file, same revision and so on. I can check the distance to the previous release type that I used, and then I can run the exact same same test. Okay, and for the fun, T1, T3. Okay, it takes 70 microseconds. So you say, hey, it's longer than CPU mode. What did you gain in this step? I didn't gain anything because I didn't optimize anything. And if you go back to the file, you will see some pragmas, the same as you have for any pre-compilation routines. With this good pragmas, you can work and tune. And in this case, the FPGA takes 1 character, only 1 routine to make the modification. Then another one, the same routine makes the 2nd character. If you just make as many conversion routines as you need, then if you have 20 characters made 1 by 1 or at the same time, then you have a reduction of 20, which is obvious, but that's what hardware allows. Reduction factors by 30, 40 are very common, because when we can multiply and parallelize the hardware things, it reduces a lot these stupid calculations that we need to make sometimes. Okay? So basically we have this conversion from mixed characters to capital. It's really hardware. I can launch the software and I can launch the debug. Maybe we can look very quickly at the debug and close with this one. So I can switch on the trace. There are different levels of trace. Let's say I want the maximum trace. Okay. In this case, I have all the details of all the exchanges with it was a MIU exchange and so on, so I can debug and say, oh, something was wrong at this level. It didn't get the register access or whatever. Okay. I didn't show you earlier. This trace mode is available in simulation with the same results. And also one thing I didn't show you in simulation, but it's obvious. If you are in CPU, the simulator is quiet. And if you're in hardware, for sure the simulator is working. Just to remind you that you can double check that sometimes you get mixed up and you don't remember exactly which one is hardware, which one is software. I think this will end up my talk. I'm very sorry I was a little bit over schedule. So maybe very quick questions.